Hey guys, so let's continue our best estimation search. So far we still couldn't find the best estimator, but we still have to find better estimators. At least when we have several estimators, which one is the better one? We solved that. We finished the sufficiency concept. If a statistic is sufficient and also unbiased, these are very good properties for an estimator. It has, if the estimator is sufficient, it has all the information necessary to estimate unknown parameter from the sample. Unbiased estimator is also very important. So if we know that the expected value of the estimator equals to the unknown parameter, so it's a good thing actually. So we want to estimate it, and the expectation is the same as the parameter itself. Consistency also nice property, so we know that when an estimator is unbiased and also consistent, so the variation of the estimator is low when the sample size is high. In that case, so this means that when we have a large enough sample, we know that our estimator will not deviate that much, so it will give us close values to the parameter. Okay, so still we couldn't find the best estimator. But we have just one property to have the best estimator actually. This property is completeness. So if our statistic is complete, or the family of PDF of the statistic belongs to complete family, then this will guarantee that that statistic will be unique statistic. So as I told you before about the several family of PDFs. So one of them is the complete family of PDF. We will see another one in a couple of weeks, I think. So we have to start with this completeness approach. But before that, let me give you another definition. When we have a sufficient statistic, it has all information to be able to estimate the unknown parameter that's in the sample, right? So when we have a statistic S is sufficient for theta if the sample from this PDF gives no additional information other than S. Okay, so this is the definition of sufficiency. We have the reverse of the sufficient statistic. These are ancillary statistics. Ancillary statistic. So basically, these statistics does not have any information regarding estimation of the population. So let's say a statistic Vx as ancillary if the distribution of the statistic, okay, is just a function of x. Okay, so the distribution of the ancillary statistic is not a function of theta. It does not have any information regarding theta in it. Moreover, we can say that Vx is the first order ancillary if its expectation is constant. Okay, so if it does not give us anything regarding theta. Okay, so if we consider just the first order expectation, we have first order ancillary. If first and second order expectations are constant, we have second order ancillary. So if all of them like that, so our statistic is totally ancillary statistic. So basically, when we have such statistic being ancillary intuitively means that it contains no information about theta. So it is just the complementary of sufficiency of sufficiency. Okay, so let's look at one example. So if we have a normally distributed random variable, and let's say here sigma square is known, mu is unknown. We want to estimate mu, let's say. We'll take a sample of size n. And let's consider two statistics here. Consider x bar and s square. Okay, sample variance. So when we consider x bar, okay, so what is the distribution of that? It is still normal because we know that a linear function of normally distributed random variable is also normally distributed. So it has mean mu and variance sigma square over n. So here, distribution of x bar contains mu. So it cannot be an ancillary statistic. Okay? But when we consider s square, so regarding s square, we know that n minus 1 s square over sigma square distributed as chi-square with n minus 1 degrees of freedom. Using the fact that the chi-square is a gamma distributed random variable, s square also we can find that it is gamma distributed random variable with parameters n minus 1 over 2 and 2 sigma square over n minus 1. Okay, so as you can see, we don't have any mu term here. So s square will be an ancillary statistic for mu. So we cannot use s square to be able to estimate mu. Just reverse of the sufficient statistic. Ancillary statistic for mu. Okay? Okay, so let's look at completeness. So when we have a complete statistics, so we will see that it will satisfy this our journey to be able to find the best estimator. So we will have a unique estimator if they have a completeness property, both besides sufficiency and also unbiasedness. Okay, so completeness. Okay, so let's start with the definition. Okay, here we also assume that we start with just one unknown parameter case. Okay, so theta is in the parameter space. Here we start with an arbitrary function of x. Okay, so consider ux. It could be any function. So we keep ux as ux actually, so we don't want to replace it by one function at this point. So it's an arbitrary function of x, and the one other property of ux should be independent of theta, not depend on theta. Okay, so now consider this function ux. So let's say we want to take the expectation of ux. My cat is mewing, so come here, come. Okay, so let's say expected ux is 0 for all possible values of theta in the parameter space. Okay, if and only if, or this requires that the function itself, what we mean by ux itself, the function itself is equal to 0. Okay, ux equals 0. What we mean by that is this one, ux itself is 0. For all possible values for all possible values of x. Then we say that this family of the PDF belongs to the complete family of PDFs. Okay, then we say that the family of PDFs. So what is this family? Whatever the f of x theta is, where theta is in the parameter space. You know, we have infinitely many numbers of for theta, and for each possible value of theta gives us many different versions of that specific PDF. So we have a family of PDFs. But this family, since it satisfies this property, so we have a complete family. Okay, family of PDFs. Okay. Okay, so what we mean by that? Okay, so we start with consider an arbitrary function of x, ux, and then we are stating that start with always expected ux, and we say that it is 0 for all possible values of theta in the parameter space if and only if ux function is 0 itself for all possible values of x. If this condition is satisfied, okay, then our family of PDF is a complete family of PDF. Okay, so we always start with the given information expected ux equal to 0 for all possible values of theta, and then try to show that this is true only for the ux equals to 0 case. Okay, so this means that basically each function of x, or when we consider the expectation of all possible or different versions of functions of x, will give us some information regarding theta. Okay, so those expectations will not be 0. Okay, so we are trying to find x itself gives some information regarding the estimation of parameters. Okay, so we have also the statistic version of that one. A statistic can be a complete statistic. So when we consider a statistic here, so statistic capital T, let's say, is complete if when we consider any function of t and expectation of that, okay, equals 0. Again, for all possible values of theta in the parameter space requires the fact that ut function itself is 0 for all possible values of t. In that case, our statistic t is complete. Okay. So here statistic t appears to be the most successful in reducing the data. If we have no non-constant function of t, is even first order ancillary. Okay, so they give some information on the estimation in terms of expectations. Okay, so the expectation of a statistic is different than 0. So it should be a function of theta itself actually. So it should be not an ancillary statistic. So basically when we have ancillary statistics, also first order ancillary statistics, they have no value for estimating theta since their expectation is independent of theta. So they will not give any information for us. Okay, so let's consider an example show that one family of PDF is a complete family of PDF. Start with a simple one, a binomial example. So show that the family, we consider a very simple one, binomial family, when sample size is just 2 case. We will generalize it later for n case, where theta is between 0 and 1, is complete. Okay, so the question is, so basically we know that it's complete, but you have to show that, or the question can be show that whether this family of PDF is complete. Okay. So basically, to be able to show the completeness, we always start with the expectation. Expectation of ux equals 0 case. But if the question is show that the family of PDF is not complete, then you have to consider a function of x, one UX function, specific function of x, and show that expectation is 0, although that function itself is different than 0. So in the case of non-completeness, incomplete case actually, so you have to consider one function. So we will see some examples regarding that. So for this question we have one hint. Actually I believe that you already know this. So when we consider a quadratic function in terms of z, az squared plus bz plus c equals 0 case. If this equality holds for more than 2 values of z, so this is a quadratic function, and usually we expect to have just 2 roots of z satisfies this equality. But if this is true for more than 2 values of z, then we have to say that a, b, and c should be 0. Okay, usually we expect to have just 2 roots for z to satisfy that, but if this holds for all for more than 2 values of z, then the coefficient should be 0. Okay, so let's first write the PDF. So n is 2, 2 choose x, theta to the x, 1 minus theta to the 2 minus x. X just takes values 0, 1, and 2. Theta is between 0 and 1. Okay, so what is our starting point to show that this family of PDF or PMF is complete? So we start with UX, an arbitrary function of x. Okay, not depend on theta, and assume that this is 0 for all possible values of theta. Actually, so all possible values of theta in this range. Okay, so let's write this expectation. Okay, so we have a binomial random variable. X is from 0 to 2. UX function 2 choose x, theta to the x, 1 minus theta to the 2 minus x. Let's open up this. Okay, so replace x by 0, 2 choose 0, theta to the 0, 1 minus 2 to the t minus 0, plus u1, 2 choose 1, theta, 1 minus theta to the 2 minus 1, plus u2, 2 choose 2, theta squared, 1 minus theta to the 2 minus 0. Okay, so what we will have, so we have u in u0, open up the square, 2 theta plus theta squared plus u1, we have 2 here, we have theta minus theta squared, right, and we have u2 theta squared. Let's write this, so this is a function of theta. Let's write this as a quadratic function in terms of theta. So the coefficients will be u0 minus 2, u1 plus u2. Then we have theta minus 2, 0 plus 2 u1 and u0 only. And we know that this is 0 for all possible values of theta in this range. So this is a quadratic function. Remember the hint. If this equality holds for more than 2 values of z, for theta in this case, then the coefficient should be 0. Then this coefficient should be 0. This coefficient should be 0 and this coefficient should be 0. Okay? Okay, so let's write them. So u0 minus 2 u1 plus u2 should be 0, minus 2 u0 plus 2 u1 is 0 and u0 is 0. Okay, so if u0 is 0, then now this means that this is 0. From here we have u1 is 0. Then here, if this is 0 and if this is 0, then from here u2 is 0. So this means that x only can take values 0, 1 and 2. So this means that expected ux is 0 for all possible values of theta in this range requires ux function is 0 for all possible values of x. So this means that the family of binomial PDFs with sample of size 2 and theta, where theta is in this range, is complete. Okay. Okay. So basically our starting point is always this one, and we have to end up with this one, and this satisfies, then we have a complete family. Let's see one example which shows that the family of PDF is not complete. Okay, so let's say we have a uniformly distributed random variable with these in this range minus theta to theta, and the question is, show that this family of PDFs is not complete. Okay, so in a not complete case, we have to consider specific form of x. So we have to consider one function of x whose expectation is 0, but the function itself is different than 0. So what we have to do, find at least one non-zero. If you can find just one function, it will be enough, then ux, such that expected ux is 0 for all possible values of theta here. Okay, but ux is different than 0 for all possible values of x. So we have to find such a thing. Okay, so the starting point for such cases actually just consider expected x. Okay, so choose a very simple one. So choose ux as x, and then see what is the expected ux or what is the expected x. So we have a uniform distributed random variable in this range. Okay, so the mean will be 0. So when we choose ux function as x, although x is different than 0 for all possible values of x, we obtain this expectation as 0. So this means that this family is not a complete family. Okay, so for all theta, positive theta, so although here, ux is x is different than 0 for all possible values of x in this range, its expectation, this is x, is 0. So this means that for all possible values of theta, this means that this uniform family, uniform minus theta theta, where theta is this one, is not complete. Okay. Okay. So let me stop here. I will continue with more examples.